Here's a walkthrough video for the Lab 3 position control lab from the Quanser system. Okay, so the whole point of this lab is to tune a proportional derivative controller to maintain a certain angle. All right, so you're given an angle, you're hitting an input that says go to that angle, and you're looking at the response. Okay, so we've had some theory, we have a model for this, and we'll go into that a little bit more, but you'll end up being able to look at the model and from that determine certain system responses that you can, hopefully meet, right? And so examples of that would be how much overshoot and what is the peak time for, how long does it take to reach that overshoot. There are other system responses, but that's what's going to be the focus of this lab, to show you the point of how you go through the design process to shape the response of your output from your system. Okay, so they make the point that this is a quantitative approach, but it generally only provides you with a starting point, and because we've talked about this several times, all models are wrong, some models are useful. Okay, so by that we mean we have this linearized model for this motor controller, and it's not going to take into account everything. So sometimes there are unmodeled components. They talk about that in this statement. And so that results in you needing to make some manual tweaks at the end. Okay, so I think a natural question would be, well, why can't I just start to tweak it from the beginning? And that's true. For this simple example, you could probably not do any of the modeling, hook this up into the right configuration, and have no reasonable chance of it working. That's because this is a pretty simple example, and the DC motor is fairly easy to model. Okay, but if the system gets more complicated, it becomes harder to do just a guess and check, and so it's important to go through a systematic way. Okay, so some of the key concepts that you need for solving the problem is, first of all, we know what the second order transfer function of a system looks like. And from that, we can look at those parameters that you see here, omega n and zeta. All right. And that will let you tune the response by getting your transfer function fit into that particular kind of template so that you get the right system response. Okay. So we're going to apply an amplitude A to a second order system, and we know what happens with that. We get this type of response. So A is the desired level that we're trying to hit. Okay, so we'll mark that there. And then at time t0, we apply the reference input A and look at the response. So the response is tracking up towards A and actually overshoots it, comes back down, and finally settles out with zero steady state error. Okay, so in this particular case, we're trying to control how much overshoot that we have. Okay, and so we're looking at PO here is percent overshoot. Okay, and then we're also looking at a response time. If this were real slow, it would maybe do something like this. All right, and so that's a slower peak time. All right, so we want to still have a certain peak time that's specified, and that's what you're working through on this example. Okay, so the peak time is the difference between when you hit the maximum based on when you start. Okay, so if you don't start at 0, you have to subtract off T0. Okay, so one thing that we know from this course is that we've done some analysis of second order systems, and you can come up with the percent overshoot as a function of the damping ratio zeta. All right, so this is an important formula. All right, that gives you a bound on zeta. All right, and then the peak time is going to depend on omega n, all right, and zeta, but zeta is really a shape parameter, so omega n dominates this. All right, so you're going to have percent overshoot constrained by zeta, and then from there, hit the peak time by changing and solving for omega n. Okay, so that's the setup, all right? And what we worked on in the previous two labs is a transfer function between output theta and input voltage to the motor, Vm. Okay, so Vm is the thing that we're using to control the motor. We change the voltage to the motor and the motor spins, all right? Now, we're setting up a slight variation on classic PD control in this example. And the variation comes from the fact that you're going to tap off the output theta m. Okay, you're going to tap that off here and feed this into the derivative, okay? And apply derivative control from there. That's a little bit different because normally we would apply derivative control on the error signal. But, it changes the way the scale constants work, but it's essentially to the rate of change of the speed of the motor. And so it's would still be considered PD control. All right, so from here, I'm going to want you to be able to derive this equation. I'm not sure if they say to do this in the instructions, but I definitely am going to give you, want to see this. Let me check if they ask for that. No, they don't. So I'm going to put that on your midterm exam. All right. So deriving this transfer function is an important step, right? Because now that lets you see it here. We're saying this is the second order system, and from there we recognize the patterns, all right? And so we're trying to relate Kp and omega n and zeta and Kd, all right? So we have on, the controller design, we have Kp and Kd, and somehow those result in omega n's and zetas, all right? So the time shape of the response drives omega n and zeta, and then from there, that gives you back the gain constants that you need. Right, so that's the point of this lab, is to show how that works. Okay, so we're going to start off, and you're going to assume that this is given. All right, we've already done labs to get you in the ballpark. Maybe your answers turned out differently, but let's go with this, all right, as the model. Okay, from there, the lab is just working through and figuring out, how the equations work. And so you'll answer from equations 4 and 5, you'll choose the omega n and zeta parameters. Okay, and from there, once you have those, they give you the right time response. You plug into the next formulas and you get the Kp and Kd gain constants. All right, and so you're going to go this and work through it, plug it into the model, use the gain sliders to start and simulate that response. Okay, and so answer the questions, work through the lab, and you'll see that the hint is you're probably going to have to tweak this a little bit after you're after you've applied the linear model. All right, so that hopefully helps you walk through the position control lab. As usual, give me a shout if you have any questions.